Hello and welcome to podcast number 49. We're going to finish off the Alkyne reactions and come up with an spider chart and then synthesis suggestions. But the last couple of reactions we want to do are hydrogenation, hydroboration, or hydrobromination, I should call it, and ozonolysis. So we'll look at these. We did hydrogenation in the early reactions, but just want to revisit it when we start looking at our spider chart because it becomes a uh, critically useful reaction for generating stereospecific organic compounds. Okay, so let's get rolling. So hydrohalogenation is the addition of a hydrogen and a halogen. So we did this with an alkene. We added HCl or HBr across a double bond. If you recall, that was a Markovnikov addition where the H protonated the alkene first, choosing the less crowded or hydrogen-rich side. H goes where H is. And then the halogen, the Br, the Cl minus, went to the other carbon, the one that's more crowded, but happened to have the carbocation in that form. It ends up that the mechanism for how it reacts with alkynes extremely different. And so what they found is the optimal uh, kinetics actually involved a 2-to-1, not 1-to-1 ratio. So um, through a series of isotopic studies and spectroscopic studies, they discovered that it does this absolutely bizarre cascade where the electrons come off from the HBr, makes sense, acidic conditions that would happen, comes a Br minus, which coordinates on the more substituted end, while simultaneously the pi bond here comes out and picks up an H and kicks out a Br. So it is not the same Br minus coming back in. It actually is an HBr that is nucleophilically attacking. So it's just kind of neat how this works, if you will. But by doing isotopic study, by making the right combination of deuterium and bromine 81, and let's say hydrogen and bromine 79, they could see how it added across, like what the combination was, what the isotopic results were, and then also by changing the ratio. If this is your rate determining step, the formation or coordination of this, then if you had a 2-to-1 ratio, that's what you show kinetically. So hopefully this seems fine. You form this weird transition state, and ultimately you add in a anti-fashion. So that's the other thing that comes out of this. The pi bonds are such that you coordinate in this fashion, where the bromine goes on bottom and the H goes on top. And it could be H on bottom, bromine on top. But the point is you go across and the Br adds on the more substituted carbon. Okay. Never going to ask you to draw a mechanism for that, but just know that it adds in a very coordinated fashion. Okay, so second equivalent of HX can add to the haloalkene, meaning you can add HBr across this as well. So you want to be careful that you don't accidentally get dibromo species if you want to stop at this. It all depends what the target molecule is. The mechanism does not go through a carbocation. It's too unstable. So you cannot have a plus charge on this alkyne in a very stable fashion. Just doesn't work out. Okay. All righty. So that's one of the reactions. Halogenation of alkynes. So if I were to add Cl2, like we do to an alkene, then it will in fact add in a trans fashion, just like it does. But that can also rotate midway to form this. So keep in mind that if they're both trans, or both cis, you've done the same thing. But you end up with both those species formed. This one's going to be the more favorable one because it's less steric hindrance, but you can also get this. This would go through the same coordinated mechanism. If you add more than one equivalent of Cl2, then you start getting complications with multiple additions. But again, it always adds to the same carbon, ClCl and then ClCl. Okay. Works with Br2 in CCl4 as well. And then the last alkene reaction I want to apply to an alkyne is ozonolysis. Ends up, it does the same thing, but now all three O's are going to have a place to go. So I no longer need dimethyl sulfide to pick up the third O. I can just do it in water solvent. Just like we saw with the alkene, it's going to cleave the double bond there. Not going to go through the mechanism, but it's very similar to what happens with an alkene. So in this case, the triple bond is being broken. I've drawn two up and one down because that's going to give me a hint of what forms. O has a go at every break point. So O, because it's only one bond, it has to be an OH. O and OH. So you end up getting two carboxylic acids. So whereas we got a ketone and a ketone, or a ketone and an aldehyde, when we did it on an alkene, now we have to have an acid. We have to have three bonds O because we have three bonds being broken. Not that challenging, but enough that I want to just, I know, make sure I have this pool of reactions. So I'm going to actually go out of sequence. The spider chart would probably be pretty useful now. So you have the spider chart in front of you. You can name that reagent. But I want to go in, I guess, reverse order. Play the game first. But here's the thing that you have to get used to when you take organic chemistry tests. They can present the, I don't know, reaction knowledge questions, for lack of a better word, in three different fashions. The first way they can do it, they can give you a reactant and say, predict the product. They can also give you the product and the reagent, the common reagent that does it. And you have to figure out what the organic molecule was to begin with. Or in this case, they give you the product and the organic molecule, and you have to figure out what reagent. Okay, so the key thing, we went from a triple bond to a double bond, and we added just one Br, so it could not be Br2. So if I said Br2 in CCl4, that'd be wrong because you have a Br there as well. So that couldn't be it. But it does have to have a Br in it. Ends up HBr. The Br goes on the more substituted carbon, as we saw in that weird mechanism. So this is simply HBr. Okay. In this one, we have the same group here, but we got rid of an H and put a CH3 on. This is that reaction we already knew before we even stepped into this grouping, the alkyne reactivity. We knew this from SN2. Deprotonate it, make it a good nucleophile, and then tack a methyl group with any leaving group you want. So CH3 is replacing an H. So first you lose the H through an acid-base reaction, deprotonate it, and then you replace it with a C. So deprotonate, and then C with some alkyl halide form, so some halogen on there. So for lack of better, something better, again, it's got to be strong enough. So N with a negative charge like LDA or sodium amide, or butyllithium and butyllithium, some variation of that as well. And then I chose a Br here, could have easily done an iodine, would have worked with a chlorine as well. Any halogen I can displace. So this one, we also saw this reaction where we get an aldehyde. Aldehydes are the result of tautomerization of an enol. So that means this first formed an enol. And note that the ring is attached, so I have carbon 1 and 2, and not nomenclature wise, but just identifying, could have done X and Y or any signifying. The O is going to the less hindered side, so it's anti-Markovnikov, which means I need the anti-Markovnikov reagents, which would mean I need boron. But because I'm dealing with an alkyne, again, it's not as selective. So I can't use pH 3 because it's going to have too much impurity of the wrong compound. So we start with the already bulky group on the boron, replacing two of the H's. So there's only one H left. So it's a 1-to-1 equivalent of this compound and 9 bbn. So 9 bbn in a 1-to-1 ratio. So 1 mole of this to 1 mole of this. And then the workup, just like it is with BH3, is peroxide under basic conditions. And then tautomerization would just proceed under those basic conditions. More name that reagent. So let's say we take that one molecule we made earlier, where we took the H off and replaced it with CH3. These are trans, which means it's added H's trans. So Lindlar's catalyst adds it cis. So that would mean I need to add it in a anti-fashion, which requires a sodium in NH3. Only works on an internal triple bond, not on a terminal. The same compound we made in previous step. In this case, the two H's are cis. So this we would use Lindlar's catalyst, which again is palladium with barium sulfate or barium or calcium carbonate. I'm just going to use the word Lindlar's catalyst because it actually isn't as clearly one compound or another as many other catalysts, but it works. So Lindlar's catalyst is good enough. So this same thing, I've converted alkene to a carbonyl. So just like it was on the last page, there must be something going on with an enol. So I'm going to get rid of this to give me a better educated guess. So if that's my enol, that means I have this carbon, I'm going to call it 1 and 2 again. So 1 and 2. It's going on the slightly less hindered side, but reality is they're both carbon, so it's not like an H versus bulky alkyl group. So it's not going to be as selective, but again, I want to make sure I use a reagent that's going to preferentially add the O to the less crowded side. So again, this is a job for like, well, I could do this, and I'm going to say this is fair enough, in that it would probably get 60% of this, but you would get the ketone here as well. I could also use 9 bbn and get this as well. So both those reagents would work. So because I used 9 bbn earlier, I'm choosing to do this. But if you were to put 9 bbn followed by peroxide, that would work as well. So let me get rid of that. And now it's time to take all these reactions and try to fit them together. What's recommended for this spider chart is show that you can take a terminal alkyne and turn it into a internal alkyne by deprotonating the H and then reacting it. And I chose a C3Br. Again, it could be iodine. This could be sodium amide and NH2. Could be LDA. Could be N-butyl lithium. Could be 2-butyl lithium. Many different ways to do this. So that's one internal reaction. And now I'm going to do spider chart based on these. So H2 Lindlar's catalyst could work on this one or this one, either way, but it adds it in a cis fashion, H2 and PD. When I forget to put the poison in there, it's going to completely take it down to the alkane. So the Lindlar poison is important. This only works on internal. If I do it on terminal, I deprotonate. So make a little note. This reaction only works on internal. So internal only. It cannot work on this over here. If I had HBr and CCl, I'll add H and a Br trans to one another. And again, this could be on either of these. If I had Cl2, it adds 2 Cls. If I had Br2, so I'm just using this, I could have also used Br2 if I wanted. Could use HCl on this one if I wanted. When I have excess Cl2 or Br2, it adds 4. Want to use R2BH, so 9-BBN is the perfect example, followed by peroxide. I get the antimarkovnikov enol, which in turn will tautomerize into the aldehyde. This, again, can react with either one of these. and you end up with a ketone. And then finally, again, same reagent. If I do it here, the ketone can go on either side. So when it's terminal, you end up getting it on the more substituted side. When it's internal, it can go either way. And that's why in the previous example, um, I didn't, the way I did it probably wouldn't be as good a yield as had I done the 9 bbn method. Okay, so one last one, ozonolysis cleaves it into two carboxylic acids. Lots of reactions, but if you compare this to what you did for the alkenes, not much different. Okay, you're going to have to use these in synthesis and predictive products, maybe a mechanism. Um, Depends on like what ultimately your professor asks. And if I happen to be your professor, I probably won't emphasize that mechanism because there's too many others. The enol mechanism is a definite keeper because it's going to be so prevalent in other parts of organic chemistry. So we have reached the end of yet another Toddcast. So thank you for joining in, and I will see you at a future Toddcast. Bye.